Good morning, everyone, and welcome to our Mechatronics education webinar in which Dr. Krovi, Michelin Endowed Chair, Professor of Vehicle Automation at Clemson University, will share his personal experiences from almost 20 years of developing mechatronics and robotic courses. My name is Susanna, and together with Dr. Nima Lotfi from the Southern Illinois University in Edwardsville, we will be your hosts and moderators today. Now, let me introduce our presenter, Dr. Krovi. Professor Krovi, as I said, is the Michelin Endowed Chair of Vehicle Automation in the Departments of Automotive Engineering and Mechanical Engineering at Clemson University. He received his PhD degree in mechanical engineering and applied mechanics from the University of Pennsylvania. His research activities are focusing on the power of the many, both robots and humans, to extend the reach of human users in the dull, dirty, and dangerous 3D environments. These efforts at analyzing and realizing the potential of distributed robotics and human-robot synergy has unlocked the new opportunities in wide-ranging applications in plant automation, consumer electronics, automobile, defense, healthcare, and surgical simulation arenas. And I'm pretty sure we will hear much more about it during the presentation today. Dr. Krovi's work has been funded by NSF, DARPA, ARO, and numerous other state and industrial grants. And he has taken a significant leadership role in robotics research and education and within the organization as ASME and IEEE. And that's why we invited him to share all these insights and experiences with us. So with that, I will pass the screen and the microphone to Dr. Krovi and let him walk us through the 20 years of his work.
Thank you, Susanna, for the kind introduction. It's a pleasure to participate in this webinar. And I think when Nima and Susanna first approached me, it gave me an opportunity to sort of think back about all the work that we had to do, we had to put in place as we were pursuing our research efforts. So it's the underlying coursework and the projects that went to preparation of the most important piece, the human capital, the talent. So I've had the opportunity to work in a variety of different areas. Right from the very beginning, I think my website at Buffalo was mechatronics.eng.buffalo.edu. Unfortunately, I couldn't get the same website out here at Clemson, still working on it. But over these many years, I've worked, as Susanna pointed out, in multi-robot cooperation, medical surgical robotics, haptics, and teleoperation. And the one common theme in all of these is that it's humans working together with robots to do these interesting things. So what I'd like to do today is give you a little bit of an overview of what motivates the research, which in turn drives some of the educational offerings. I think the first few slides are intended to be a broad overview. Some of these ideas are well known to most people, but nevertheless, I think it's important to reiterate the fact that machines and mechanisms have been around since prehistory. But it wasn't until the first industrial revolution, when steam power came in, that you had a portable source of power that you could turn on and off, which then improved in the second industrial revolution with electrical energy, the third industrial revolution, where you could now modulate this power electronically, And in the current age of cyber-physical systems, that ability to modulate power in distributed systems has in by some people's claim unlocked the fourth industrial revolution. But I always try to showcase to the students that there is a virtuous cycle that one needs to keep in mind. First, there is creating capability. From that capability ensues convenience. And then from that convenience, there are a number of commercialization opportunities that get unlocked. And so once we get this virtuous cycle rolling in the right direction, it leads to immense opportunities. Sometimes in the innovation space, people try to look for the commercialization aspects before they even develop the capability. And I think that can prove to be somewhat challenging. So looking at robotics and automation over 50 years now, I think we're coming closer to 60 now. It has helped to extend human reach, to manipulate objects as well as physical quantities in different spatial and temporal scales. But if you were to ask somebody, was there one significant turning point in when this occurred? People will point to, of course, the science and technology advances. They'll also talk about the triple convergence in computing, communication, and perhaps most importantly, the integration that comes about because of miniaturization. But I often end up quoting Tom Friedman in his book, when he talks about the world is flat. My argument is that the robotics world has been similarly flattened, and that there is no one single point in time when these advances that you could say that was the critical point in time. So in addition to the earlier triple convergence that I talked about, there is one very critical evolutionary driver that often does not get reported as much. And to me, I call this the digital redesign paradigm. Others might choose to represent it differently. But it comes from taking essentially monolithic systems that may have had subsystems, but these subsystems are connected by a physical connection, and replacing them with breaking them apart, replacing them with analog interconnections, and in the recent era, now with digital interconnections. In doing so, you often end up creating a loosely interconnected dynamical system, and oftentimes at face value, you're compromising performance. But what you lose in performance, you're able to regain in terms of flexibility. And the numbers of examples for these are many, but I'll use an automotive example where if you think about a drive-by-wire system replacing the traditional steering wheel, you'd have needed a high-resolution encoder and a high-fidelity motor, even just to create the same feel of a mechanical steering subsystem. But now that you've broken up the system into pieces, you can take that steering wheel and put it anywhere you want in the car. The steering wheel you could replace with a joystick. You could have two steering wheels. Your second steering wheel can be in Tokyo. Your second steering wheel can be a computer. And so that the functionality that you gain, the flexibility that you gain by breaking up that monolithic system now creates this opportunity. Further, it also creates a natural opportunity to infuse information technology into the traditionally opaque mechanical world. and to then also be able to get insights into that mechanical world. And so this has been the theme of a lot of my research activity in the past. And I think as we look around us, there are an incredible set of applications that have been developing that have all sort of implicitly built upon this theme. So over the years, we worked in a variety of different areas, and I suppose I could give several research seminars on that front, but I just wanted to quickly show you some of these vignettes. They range from cable-based manipulation to video-based human activity recognition to surgical robots to musculoskeletal analyses, and now more recently self-driving cars. And I'll touch upon all of these as they relate to the courses in the rest of this presentation. So I have two major courses that I'd like to discuss in today's discussion. But time permitting, I might be able to add one more towards the very end. So the course that I started out with was MAE 476, 576, which is called Mechatronics Design. This was a course that I had first initiated when I was teaching at McGill, and then when I transitioned to the University at Buffalo, this became a part of the curriculum. And as people familiar with course introduction, it had an initial name of MAE 505 Mechatronics. And so if you see the 576 and 505, it's alluding to the same course. So this course was introduced as a mezzanine course, meaning it was open to senior undergraduate students as well as incoming graduate students. And the goal was to now give these students working familiarity with microprocessor and electronic technologies, but not in a vacuum. It was intended to help support the design and control of mechatronic systems. So in any course, somebody has to make an initial decision as to what the topical coverage of the course is going to be. And so in a course like this, there are many topics that one would want to cover. But from a pedagogic perspective, I wanted to talk a little bit about why we made some of these choices. So I think I've had some trouble with one of the GIFs not showing up here, but the classical mechatronic challenge, I think, that most people talk about is one where on one hand you have contributions coming to the field of mechatronics from many of the traditional disciplines and subject matter coming from the traditional disciplines. But even within the mechatronic system, because you have the mechanical, electronic, computing, and algorithmic control components blending together, it becomes an interdisciplinary and often a multidisciplinary and often an interdisciplinary field. So from the perspective of the class, then, one of the ideas that I would highlight is the digital redesign paradigm that we've talked about in an earlier slide. But I would also try to emphasize the need for making sure that we follow the virtuous cycle. So these were sort of two themes that I try to highlight in the class. And to do this, I often started with relatively simple examples. So we would take something like a thermostat, and we would look at the history of evolution of the thermostat. So the traditional mechanical solution for the thermostat might be to use a bimetallic strip that makes and breaks contact, that then allows for control and regulation of let's say, the heating in an electric iron. But in this context, you can see that we would use this as an opportunity to discuss requirements, of course, but then how you could take those requirements and then draw specifications based on functional performance. So a thermostat such as this could now only regulate temperature between plus or minus 5 degrees, for example. If you looked at other examples of the evolution of the thermostat, by adding a mercury switch coupled with a bimetallic strip and using this coupled with relays, you are starting to explore an approach where you're no longer directly controlling the power flow, but you're modulating the power flow. And so these are ideas that then become very useful as we talk about microprocessor or microcontroller-based regulation of power. And so the ultimate example in this sequence would then be a microcontroller-based system that now the microcontroller also allows innovative features such as keypads, LCD displays. And once you have this human-machine interface capability, you could start to regulate temperature. You could start to create set points. You could create variable set points at varied times in the day. You could now regulate power, regulate the temperature, perhaps to a better fidelity than what was possible. And I think one theme in all of this was this system was now intended to help automate a dull, dumb, dirty, and potentially dangerous job. But this then gave me opportunities to start people's thinking along the lines of, are there other things that are ready for digital redesign? And so shown here is a small subset of things that have already transitioned into the digital redesign phase. But it also gave opportunities to now go back to this original example and say, what do you anticipate is next in this? And so even back in the day in 2000, it wasn't such a stretch of imagination to tell them, what if you could put a little web server into this? And that would allow your smartphone to then connect to a system such as this. So it was also helpful to now create opportunities for future improvement of the digital redesign. But to try to focus things back towards my course, I would use a robot, and in particular a bump sensing robot, as the core example to highlight the fact that this is now a system, blending mechanics, electronics, control, and computing, but with some constraints. The constraints, of course, are on resources. The constraints now come from the initial design selection. And perhaps the most important constraint is that for this system to be effective, it had to perform in real time. So coming back to the course organization, that allowed me to highlight some themes in my course. So the overall course was developed with an instrumentation systems flavor. We would look at things like sensing and actuation principles, but then the fact that even sensors and actuators could be zeroth, first order, or second order systems that require calibration, both at an individual component level, but when you daisy chain them, an end-to-end calibration was critical. We ended up deploying a lot of this using some of the kits that were starting to emerge in that time frame, things like the basic stamp and the pick kits. And so this gave our students an opportunity to implement hands-on some of their core ideas. But the theme that we ended up using was that was that of design. And so let me take a second to highlight what I mean by design. So in my mind, design is a systematic creation of multiple options, followed by a systematic evaluation of these options according to certain functional criteria. And then, most critically, it was the systematic elimination of surplus options so that you're left with an end-to-end system. So if you applied that design principle now even to the course here, what I was able to do was to find an incredible set of resources that were starting to become available on the web. And by selecting different, let's say, individual experiments and focusing on a synthesis of these to create a system, that gave me a rich field within which I could now deploy my course. So from a course organization perspective, we would have lectures that would touch upon some of the key theoretical concepts. But then we had labs. They ranged anywhere between 3 to 5. Each was about 2 to 3 weeks long, and they were based on. And I'll have a slide on this to follow. But they were modular sublabs that I could then cascade one on top of another towards the end goal of creating a final project. Through this process, again, for students, we would emphasize documentation, for example, and so every student team had to now submit lab reports. They had to do a demonstration at the end of the lab. And for the final project, there was also an oral presentation. So as you can imagine, team-based activity and especially loosely structured activity can be quite, can rapidly start to disintegrate. And so we would have check-in points via weekly emails, and on the weeks when lab exercises were due, that would take the report would take the role of the weekly check-in emails. So just transitioning now, and just to give you a sense of how we would deploy the core portion of the course and some of the theoretical aspects of the course. I think the basic frame that I approached things from was, as I said, the instrumentation perspective. So our goal as engineers, not necessarily just mechanical, was to be able to measure the physical world, things like position, force, vibration. But because we are doing this with a microprocessor or a microcontroller, there are some things that microcontrollers are able to do better, which is measure voltage differences, currents, resistance, frequency, and time. And so a sensor is essentially a transducer of one form of energy into another. And so this sensing principle then gives rise to a number of these potential sense. Let me see. Gives rise to a number of these sensors. But I think the taking that core idea and illustrating it in the context of a simple rotational sensor example, we would then do deeper dives into specific types of sensors, for example, rotational sensors, and how you have the resistance change principle now forming the basis of a traditional rotational sensor, which would then have to be interfaced with an analog to digital system, conditioned, and then read into the microcontroller. But it gave us opportunities to also look at digital redesign of the sensor. So, for example, using a Hall effect sensor, you had the opportunity to create a rotational sensor that was born digital. And so whether you chose to do this through a Hall effect sensor or through a photo interrupter or alternately a photo reflector, gave us opportunities to then look at other principles such as the digital encoder. So the core theme in this case was, of course, digital replacement of analog functions. Similarly, when it came time to look at actuators, while we were able to look at the spectrum of actuation and their preferred actuation ranges in terms of speed and payload, we transitioned the discussion to intelligent actuation subsystems. And so with the RC servo as a prototypical example of how you could create an intelligent actuation subsystem, and then transition the discussion to networked systems of this sort, and the ability to now have a dedicated subcontroller that, such as a servo controller, that would now tend to multiple such intelligent actuation subsystems. Similar ideas in the computing space, where the core requirement of the computing was, of course, to take different types of digital signals, analog signals, human inputs, and of course the noise that comes with any one of the above three, and process this to be able to give different types of digital outputs, analog outputs, and human machine interface outputs. And so the compute power that was required to perform this in past eras used to be in the microprocessor. But as we transition to the microcontroller frame of things, the ability to now network these in a small area network using interconnect protocols such as an I2C network or an SPI network was also a theme that we brought out in this course. And so when we then start to use the bump sensing robot as an example, we could start to illustrate where some of these decisions had to be made, in some cases by the vendor, but in other cases by the students themselves, as they chose to implement the mechanics, electronics, control, and computing. In particular, when we looked at some of the different labs, we see that rather than make it just a plain vanilla interface, an LCD screen, a matrix keypad to a microcontroller, as is traditional, we tried to create a functional outcome from the lab. So lab one in this case was build me a digital stopwatch. In other cases, we've transitioned that lab to say, build me a burglar alarm system. For teaching analog to digital conversion and digital to analog, we would use the focus of building a digital multimeter as an end-to-end system, subsystem example of that would allow them to now discover some of the trade-offs between implementing things in hardware versus implementing things in software. So I could go through this list in detail, but I think the core ideas of how do you interface external devices, how do you do analog to digital conversion, how do you do pulse encoding, software decoding, how do you do control, and the options to offload some of these to sort of dedicated intelligent subcontrollers was a theme that we. So as we come into this final project, this was an opportunity then for students to now integrate things. We intentionally asked for this to be a networked system. And we gave the students the option of making that network either a wired or a wireless system. In the wired case, they would just have a really long set of cables that would connect, and you'd use an SPI or an I2C interconnect to the rover. But I think our preferred option was to try to deploy this using a wireless system. And so what you're seeing here are some examples of the types of projects that students who had no prior background in any of these were creating while working in teams in the context of the course. And we were fortunate
on Sunday.
Just fine.
To have some news coverage of this.
All right, thanks, Don. Well, for college students, this is a time of year when final projects are due and their whole grade may be on the line. So you'll appreciate the drama that built late this afternoon in UB's engineering lab when students had to put the robots they created through their paces.
This is our home station. Initially,
Students in a mechanical engineering class at the University at Buffalo are learning how to make life more simple through robotics. But creating these machines isn't easy.
we are modeling the motor by using this equation, and then another part is the electrical equation.
Sound complicated? It is. The students learned complex equations like these and created 5 different robots, each with its own simple task.
The robot that you see there is intended to pick up little balls from a home location and move it to another target location.
When we hit a button on the base station, it sends a signal to the robot, and it will tell it where we want it to go.
One group created a model similar to the Mars Pathfinder that navigates through obstacles.
Just in the interest of time, I'm going to transition now to what some of my current research is about and some of the courses that we are now developing in this current research. Again, I apologize for some of the blur in the screen, but as over these past 20 years, one of the things that we've seen accelerating just in every aspect of our daily life is the improvement in networking. And so the automation paradigm that now allows you to do sense, think, and act in real time, all of a sudden has an expanded preview that comes through the networking. But the ability to now engineer new capabilities in aggregated systems of systems is the one where some of the bigger challenges come about. So in our case, from a research perspective, we are looking at on-road automation for things like self-driving cars, off-road automation for things like precision agriculture, and manufacturing shop floor automation for logistics and so on. But and in terms of the research capabilities, then we're looking at building systems that are small scale, that are mid scale, and at full scale. So what you're seeing on the screen are just a range of some of the research projects that we are undertaking at our Clemson University International Center for Automotive Research. We're also looking at deploying several of these now for the manufacturing shop floor. And I think for people who are working in the area of robotics, it's now an interesting time for mobile manipulation, where the mobility and the manipulation capabilities can now be harnessed to get the right part to the right place at the right time. So if somebody is interested in this, I'm happy to talk to them about it afterwards. But the question that I wanted to sort of use these slides to provoke was, as we start to now build the capabilities of our students into developing these types of systems, clearly there's a new class of capability that is needed. Even within the automotive industry, as we look at how the industry has moved from a subsystem-based approach to a system-based approach, there's been an explosion in complexity. So just to give some reference to where the industry is at these days, this was a IEEE Spectrum article where it talks about the car having 100 million lines of code, and this is just a modern day car. And to place it in context, this is now more lines of code than the Boeing 787, the Mars rover, and the F-22 Raptor combined. And so even getting our students to be able to tackle this complexity is challenging enough. But now as you look at expanding the preview of a car to include different kinds of autonomous capabilities and transitioning it all the way to a smart city vehicle to infrastructure automation, there's a fundamental disconnect. And so it was to look at how we could still work within the traditional paradigm of how systems deploy in the automotive industry with the well-understood V model. We were finding that from a competence perspective, people were not matching the growth in complexity. So for all these purposes then, we started to develop a set of courses that I'll talk about. But one of the key features that I wanted to highlight with this slide was that almost inevitably, we would have needed to leverage a variety of existing middleware frameworks. So from the perspective of courses then, we've now created new curricula in perception and autonomy. There are a set of 4 courses that we currently deploy. I'm going to do a deeper dive into the Autonomy Science and Systems course, but if people have an interest in any of these other courses, I'd be happy to connect you with the corresponding professor of the course. So in addition to the courses we are developing here, we're looking at linkages back to our main campus courses. And doing this development was not intended just as a standalone effort. It also helps us with some of our outreach activities. So we're able to organize high school and middle school competitions, as well as a number of other undergraduate outreach events. So with respect to the course itself, this work was represented in a publication in the recently concluded IDETC conference. And there are more details in than what I'll be able to show in today's discussion. But our core premise was, how do we empower graduate engineering students with proficiency in autonomy? So I have about 15 slides from that 15-minute presentation, and I don't think I'll be able to get through all of them quickly enough. But I'll try to give you the highlights of this, and we can follow up with other details. So from the perspective of autonomous driving, there are a number of areas that people are looking at, but our focus was on the technology and in particular the hardware. But from the perspective of diversifying the curriculum, if you looked at the autonomous vehicle space, there are an incredible number of opportunities for people who have the right talent set. And so it was using that as the motivation that we developed this course. And one of the first things that we would highlight to our students is that your autonomous car is an embodiment of the sense, think, and act paradigm, just at a slightly bigger scale. And clearly, while you will not be able to develop a full-fledged vehicle by yourself, some of these technologies that you're going to learn are going to be the steps towards that. And most critically, in being able to do the down selection, our emphasis was on real-time performance. So from a classroom perspective, we adopted a flipped classroom model where our courses would be in the form of video lectures, website links, and so on. And in class, when the students come, there would be group discussions, there'd be code implementations and troubleshooting. From a topical coverage, we had to work with a cohort of students who were largely mechanical and industrial, with a couple of electronics and computer science students. So spent a significant time developing, getting them up to speed on the software frameworks, but also because they had not had adequate exposure to concepts, things such as steering architectures and kinematics, navigation, path planning, and then building your way up to layering obstacle avoidance or simultaneous localization and mapping. So we would have little modules that talked about these. From a deployment perspective, we would use a turtle bot, and in particular a physical turtle bot, as well as a software simulation in Gazebo, to help them get up to speed with ROS concepts. But then in the final project of the course, they would actually build one of these self-driving cars. And so in this case, we were very lucky to have a collaboration with the University of Pennsylvania, which had developed this F1 10th set of course modules that would let people build, drive, and race their own autonomous RC cars. And so during the course, then the first part of the course was really an introduction to software frameworks and to simulation, which we were then able to leverage in the second module of the course, which is about 6 weeks long, where people then got to try these out largely in simulation, but now with the Turtlebot as the physical embodiment. And then finally, in the final 5 weeks of the course, there was this capstone project where essentially we obtained all the components that such as the LIDAR system, the compute platform, the cameras, as individual components that people had to then integrate onto the Traxxas RC chassis. And for this, some of the efforts that the F1 10th group had done in terms of providing these short tutorials were extremely useful. And so just a week-by-week breakdown of how the final project transitioned. First week was largely about device interfacing and assembly hardware. Our week 2 was now focused on different localization techniques, and in particular, we ended up using Hector Slam largely. Week 3 was on brainstorming different control strategies. And so the Gazebo simulation with MIT's race car was the model that we ended up using. Week 4 was when different control strategies were then implemented on the hardware system. And in week 5, we spent tuning and testing their different systems. And so needless to say, I think when you have a final project presentation that involves hardware, there's a lot of drama involved in this. But I think we only had 3 groups, and so all 3 groups managed to do this quite successfully. So each one of the groups actually then, on top of this platform, were able to implement their own variants of controllers. So for example, Team A was using Pure Pursuit, Team B was potential field approach, and Team C used actually a hybrid approach. And all of this is now reported in the IDETC paper. So that was really the second course. And just in the last 2 minutes, what I wanted to do was a lot of the effort that we've talked about here was on the physical interfacing and the mechatronic realization of these systems. But I also wanted to make a pitch for the other part of it, which is some of the theory, and in particular the articulated mechanical system theory that underlies many of these mechatronic systems. As these systems become more and more complex, having a physical basis for modeling and analysis of these systems is critical. And we find that we use this quite routinely in a research context. But the ability to now also have courses that allow you to bring theory to life and empower our students with toolkits that are current industry practice is an important. So I think everyone here understands the basis of physical modeling. What I'll do is that in the interest of time, I'll highlight the fact that we used both the MATLAB Simulink approach as well as the MapleSim modeling approach. But the critical dimension why we preferred using the MapleSim was we had access to the underlying symbolic equations that we would then use quite effectively, in my mind, to be able to take some of the abstract concepts that we would cover in a pedagogic lecture and connect them to a computational implementation and then to actual hardware in the loop realization. So if people have an interest in any of this, I'd be happy to talk to them offline. We've done a number of these efforts, including things like self-paced MapleSim tutorials to enhance robotics courses. This was reported in a conference paper that then also came in a special issue of ASEE, where it won the Best Journal Paper Award. We've looked at doing model-based control as an independent study for a student that then led up to his thesis. And of course, within our own research, we've been using these model-based approaches, model-based symbolic computation approaches for everything from generating vehicle dynamics equations for large degree of freedom models, like 14 degree of freedom vehicle models, and for developing equations of motion for complex parallel architecture systems like the hexapod or HD2. In all these cases, I think in a previous era, developing those equations would have been the entire thesis in itself. Here, with the ability of using some of these modern tools, our students were able to get accurate, encapsulated, and computationally implementable models that they could then examine higher order questions, such as, does the modeling fidelity of the vehicle dynamics model allow for better haptic control? So with that, I'll stop because I think I'm running out of time.
Thank you very much, Dr. Krovi. I really enjoyed your presentation, and I'm sure the audience did as well. It's a very impressive presentation. There were a few questions that I wanted to ask you. The first one you mentioned, you talked about your course, especially the first one that you talked about. Can you tell us a little bit about the challenges that you've had in regards to teaching undergrads versus graduates mechatronics, or teaching mechatronics to undergrads versus graduates? Because most of these software platforms that you talked about, they typically have a big learning curve, such as ROS. So how did you solve this issue in regards to teaching mechatronics?
So ROS was the second course that I highlighted. Do you want me to talk about the first course or the second course?
Just in general, how did between graduates and undergrads, because graduate level would be easier to use different platforms, both software and hardware, but in undergrad there are a lot of limitations, especially in regards to students' knowledge in mechanical engineering departments, for example. So how did you solve this challenge while teaching your courses?
So that's a great question, and I think throughout this whole process of developing courses, I think the fundamental challenge that the fundamental framing of this problem was, if I were to give this as a problem to a practicing mechatronics engineer, then I typically don't have to worry about the theory and the accumulated experiences that they may, engineering experiences that they may have had, that they can now bring to bear on a problem. But with a student, the challenge is they neither have the background theory and experience, nor are they familiar with the tools. So the theory and the experience were things that we were looking to now provide in the context of the course. From the tools perspective, I think we were quite fortunate that it was right about the time when there was almost like an explosion of open source material that was available on different websites and different vendors' websites. It meant that I had to take extra time to go and curate those resources and to identify what was important. And then we would have tutorial classes almost during some of these office hours, just simply to bring these students up to speed on some of these. So let me take a quick example. In the case of ROS, the Turtlebot community has very extensive and detailed resources on how do you now implement the Turtlebot. You could technically ask your student, okay, go look through that website and figure it out. But I think being able to digest some of that information, pick out what is important, and then discuss that in these tutorials, then help them to sort of overcome that initial inertia. It also did mean a lot of work on our part. And I'm actually grateful that we've had some good TAs who were able to carry the day.
Okay, thank you. I think we can ask one more question. So you mentioned in one of your most recent developed courses, you're using the F110 platform. So can you tell us a little bit more about that platform, especially because it seems to be a very practical and useful experimental platform, but can you, I don't know if you can tell us about the cost and...
Okay, so let me quickly try to bring the presentation to that part. So this F110 platform is an output of the University of Pennsylvania, in particular Dr. Rahul Mangaram's lab. What their group had done was they had developed this as a research platform for some of their own hybrid systems work, but realizing its utility, they had also created a set of resources. And so in this case, let me show you what that might look like. A set of resources for how you would acquire all the different components of the vehicle. So you have a bill of materials, you have quick digestible types of PDF documents and video lectures that would show you all the critical steps in how you integrate that. And then finally, you had a little code fragments that you could now integrate to now get at least a base end-to-end reference model. So further optimization on this was clearly something that they wanted the different groups to do, because they've been organizing workshops at CPS Week and a number of other places. And these are now, with every workshop, there is also a racing activity, so there's a little bit of a competition. But being able to scaffold something like this now creates interesting opportunities. In their case, again, while the bill of materials includes things like the LIDAR system, and the LIDAR in this case is the most expensive component. It was about $1,600. The chassis platform was about $400. The TK-1 is about $500. So I think each one of these systems probably is about, I'd say, under $5,000. You could actually build one of these. And it may not be something that every course may want to deploy, but you have the opportunity to do some of this in simulation using only the gazebo simulation, for example. Or there are interesting other models where you could explore this in the context of an independent study. But the ability to mix and match these options is what I wanted to highlight, that if you're careful and look around, there are a number of these resources that are available.
Okay, okay. Thank you very much. We are out of time, but I really appreciate your willingness to present and talk about your valuable experience. If you could please send us this presentation afterwards, we will make it available to everyone. And once again, thank you.
All right. Thank you so much.